All right, as we alluded to there in that warm-up question or questions about what combinations mean, combinations are kind of something that goes along with permutations. Combinations are when you're making a selection of objects where you don't care about the order. Permutations is where you do care about the order. As an illustration for that, there's a situation here about people in a race. Here you have 5 sprinters that are competing in a race, so you have 5 objects, if you will. And you also have 5 objects down here, same 5 sprinters. In the first part it says, how many ways can medals for first, second, and third place be awarded to those 5 people? So you need to choose 3 from 5, right? 3 things from 5. Do you care about the order? Does the order matter here? If you're giving first, second, and third, finishing first, is that different than finishing second? It is, right? Where you do care about the order. Where order matters. Yes, the order matters. So this is an example of a permutation. Permutation is where you do care about the order. 5 objects taken 3 at a time. The symbol you could use is 5p3. Okay, we can use a formula to figure that out, which we'll look at in a second, the difference. Now I want you to contrast that with, or compare and contrast that with, if you have the same 5 sprinters, but now all you care about is the fastest 3 qualify. I know still it's nice to beat the other people and I was the first qualifier and all that, but technically does it matter in terms of going on? Does it matter? If the top 3 qualify, does it matter the order you finish? No, right? Doesn't matter. The order does not matter here, right? So here you're choosing 3 from 5, where order doesn't matter, right? Where order doesn't matter. Let me illustrate that for you up here. You have your 5 people here. We're going to call them A, B, C, D, and E. Up here you're choosing them like this. You're saying, I need a first place, a second place, a third place, but after that I don't care. It's loser, loser, we don't care, right? Not very nice, but that's the truth. Down here, do we care about the 1, 2, 3? We're just going to call them, I don't know, using X for loser there. I'll call, I don't know, Q for qualifier. You qualify, you qualify, you qualify, loser, loser, right? You don't care about the order of the ones you're choosing. Up here, we divided by, we worked this out by saying we have 5 in total, right? 5 in total. But we're dividing by, to work that out, we're dividing by the ones we are not choosing here, right? We divided by 2 factorial because the ones we are not choosing. That matched what we did with permutations with identical objects. When you have 2 the same, you got to divide by 2 factorial. If you're choosing 3 from 5, you don't care about the ones you don't pick, so you divide by 2 factorial. Now we're changing this so that we don't care about the ones we don't pick, but we also don't care about the ones we do pick, right? We don't care about the order of the ones we are choosing here as well, those ones, right? So we have 5 in total, 5 factorial. We're going to divide by 2 factorial for the ones that we don't choose, but what are we also going to divide by here now? We don't care now about the order of the ones we are choosing, so what do we also have to divide by? 3 factorial, right? The combinations formula is going to be very similar to the permutations formula, except that you're going to have this extra thing you divide by because you don't care about the order of the ones not chosen or the ones chosen, right? So this is choosing 3 from 5 where you do care about the order, 5p3. This expression down here is choosing 3 from 5 where you don't care about the order. Not surprisingly, the symbol is going to be 5c3. Okay, that's that. It's got that extra thing because you don't care about the order of the ones you are choosing as well. Okay, now I originally had yeses and nos over here. Basically, you're just rearranging the yeses and the nos, right? All you care about is 3 yeses and 2 nos. You know, this could be A, B, C, and then this is the other 2 people here, or whatever, right? But you don't care about rearranging the order of the 3 that are the ones that qualify. Okay, this is an example of a combination of 5 taken 3 at a time. The difference between those 2 here. Okay, you should maybe write something for yourself there explaining the difference between those 2 things. You can use the example of the sprinters in a race. If you want to use your own example there, you can. But I would write something in your own words explaining. Don't just say this order matters, this order doesn't matter. Use an example. Use something. Maybe think of a different example. Can you do that? All right. So combinations choosing. Here's another simple example. Letters from a word here. If you care about the order, okay. If the order you're choosing these letters in, you're choosing 3 of those 7 letters. If the order matters, you can write this expression 7p3. The expression using factorials that you can use to come up with that is orders of all of them, 7 factorial, over the orders of the ones you're not choosing. 7 factorial over 4. You can work that out. It'll give you something or other, right? 7 factorial over 4 factorial, 7 times 6 times 5 times 4 factorial, 4 factorial. You can cross out the 2 4 factorials, and hopefully somebody can tell me what that is. Never mind, it's, what is it, 210 or something like that? 7 times 6 times 5. There's 210 ways to choose 3 of those letters if you care about the orders, right? So that means that if you pick LAC, that's different than LCA and ACL and all of those things, right? These are all different. If you're talking about permutations, this is different here. What it says down here is if the order of the selections doesn't matter. If the order of the selections doesn't matter, you can use the shorthand 7C3. You're going to count it indirectly in a very similar way. You're going to say there's the arrangements of all of them. You're going to divide by 4 factorial for the ones you're not choosing. But now what's the extra thing that's going to be here? You're also going to divide by 3 factorial for the ones you are choosing, right? Because you don't care about the orders of the ones you are choosing. This number up here is what you get without this here. But now, if you know that there's, 3 factorial ways to rearrange any given 3 letters, you're going to divide by that number, right? So this is 210. No, it's not. What's the top number? What's 7 factorial? Let's put all the numbers in here, actually. I'll pause this while we come up with those numbers. So that's 5,040. This is 24, and 3 factorial is 6. The extra thing in here, this extra thing is how many arrangements for any given 3 letters you choose. There's 6 different ways, right? For any given 6, like for LAC, there's LAC, LCA, there's ACL, there's ALC, and there's CAL and CLA, right? There's six different arrangements. So you're saying, I'm going to count all of them as though I do care about the order, but then divide by that because I don't care about the order. Okay? That's important to understand. It's one thing to be able to calculate it, but it's another thing to understand how this formula works, which would go a long way, I think. There's 3 things here. This is the arrangements of all of them. This is the arrangements of the ones not chosen. And this is the ones that are chosen. The chosen ones. So then that number comes out to not 210, it comes out to 35, right? There's 35 ways you can choose them if you don't care about the order. Of course, you could just go directly with this to your calculator, but that's it's important to know how to do it both ways. The formula then, we'll finish with this formula here in 30 seconds or less. The formula is very similar. N factorial for all of them. N minus R for the ones not chosen. What's the extra thing that has to go here? If you're choosing R from N, what has to go at the beginning of that? R factorial. That's the combinations formula. It just has this different than the permutations formula. Okay?